Now we start our 28th year of the seminar Malliavin Calculus and its application with the talk of Vitalii Konarovskyi, a quantitative central limit theorem for simple symmetric exclusion process. Please, Vitalii.
Okay, thank you so much, Andrei Anatolyevich, for the opportunity to give a talk and tell you about our recent result with Benjamin Gess about the rate of convergence in the central limit theorem for a simple symmetric exclusion process. As probably you know, that one of the powerful tools to prove the quantitative central limit theorem is a Stein method. And so it works nicely, for instance, when you work with finite dimensional models. But when you want to consider the dynamics which evolves in time, usually Stein method is very complicated to apply. For instance, you can try a Malliavin Stein methods, but usually you can be unsuccessful. So therefore, our idea was to try to find another way to prove a central limit theorem for models which evolves in time. And here we wanted to use some additional property which probably which a priori we expect to know. For instance, when you consider the dynamics of particles which evolve in time, you expect that you work with a Markov process. And when you have a Markov process, you already have a generator, and it is really a lot of information. And we wanted to actually use that information to be able to say something about the rate of convergence in the central limit theorem. And so therefore, our idea was to choose probably one of the simplest model in statistical mechanics. We choose a simple symmetric exclusion process and then try to prove the central limit theorem. So therefore, today I would like to discuss an approach which we applied here and which we didn't see so much in the literature. So we could see a few other papers where a similar approach was used, but in different perspective, but not in the case of the hydrodynamical limit, which we consider here. But if you have any references so related with my talk, so please let me know. We would be very happy to include them also in our work, in our manuscript. So therefore, let's start. And I will start from the description of the model. I will work on the discrete torus, so which is a subset of the d-dimensional torus. And here, for the simplicity, we will choose a specific grid on the discrete torus. We will assume that 0 point belongs to the grid, and also we have the same number of sides in every direction. It is so this choice is motivated only by the fact that we wanted to be simple in notations and computations. So you can put here, for instance, n, but with this choice, many computations just becomes just a little bit simple. And now the simple symmetric exclusion process, it is a collection of, roughly speaking, collection of independent random walks on this discrete torus, where particles jump just independently of each other, except the case when two particles are are close to each other. So, and when a particle wants to jump to the side where is already a particle, then this jump do not happen. So, for instance, when this particle wants to jump here, so this doesn't happen. And
Vitalii, can I ask you, but the neighbor particles also want to jump? Maybe the site will free?
No, it usually cannot happen at the same time, because for every particle we have independent exponential clock, and the probability that it happens simultaneously for the same particle,
okay.
so it is equal to 0.
Okay, so now
But
we have to add that every particle has geometric clock. Yes?
yeah, sure, because we want to have a Markov process, and we consider so we think about
But
every
if
particle
we
as
have Vitalii,
continuous in time in random walk. So assuming the moment that we have exponential clocks with parameter 1.
okay.
And since we don't assume that our particles are labeled, so then therefore this fact that particles do not jump to the site where is another particles is equivalent that we just interchange two particles. So dynamically it is the same. And actually this second choice we will use to write the generator on the next slide. And now to describe the configurations of particles, we will use functions which are defined on the discrete torus and takes two values, 0 and 1. And we will write so that eta of x is equal to 0 if on the grid x there is no particle, and 1 if there is a particle. So therefore here for this picture, so the particle configuration can be written or code using the function eta, so as follows. And now also let me introduce the notation. I will write eta x and then errors in both direction y. It will mean that I just will take the information inside x or value inside x and value inside y, and I will change them. So then having this notation, we can define the generator. That way we will go through all sides on the grid, and then we write the generator in such a form. So please note here that here I already put the normalizing constant to n plus 1 to the square. And it corresponds to the case that clocks happens not in exponential times with parameter 1, but you need to divide the exponential time by n plus 1 by 2n plus 1 to the square. So therefore, already now you have a model that where we rescaled the space according to or proportional to 1 over n and time proportionally to n squared. So do you have any questions here? So
yes, there is a so-called
understand the model because later.
Excuse me, Vitalii, do you hear me?
Define it, which dynamics you want to consider, and you define the generator. You have two possibilities. Actually, either you can consider equilibrium dynamics or non-equilibrium dynamics. So first of all, let me say that I will write eta t with index n here for the simple symmetric exclusion process. For the Markov process defined by the generator given on the previous slide.
Vitalii.
And then in the
Vitalii.
equilibrium case, you assume that particles.
Vitalii, do you hear me?
Yes, yes, I hear you.
Okay, so let me ask you. There is so-called Wright-Fisher model where we have particles which persist Markov movement on the space, and when they collide, they jumps for some other place and continue motion. And this model works on general space. What is did you think about the relationship with Wright-Fisher model?
Disconnected.
So Vitalii is disconnected, yeah?
Yes.
Okay. Oh,
Let's wait.
yeah, surely, we have to wait. Georgi, do you see that he is trying to connect?
Now, no, not.
Mhm, mhm. Okay, let's wait. Mhm.
Okay, I'm so sorry. It's the first time that at the university something happened with the internet. Now I use my mobile internet, and I hope you can hear me well.
Yes.
Okay, very good. I really apologize for that. So share the screen and control. Okay, Andrei Anatolich, did you have some question?
Yes, I have a question about the Wright-Fisher model, where we have a number of particles which persist independent Markov motions along the space. When they meet, they have a jump to other place in the space. This model was written in different framework, for example, even for metric space. So did you compare your model with those? Is it essential that you have lattice here? Because
I will tell you later about the possibilities of application of the approach that we use here to other models. And we didn't consider different. We only considered also the zero range process. I will not tell what it is, but also it is. So here you have just different dynamics. You also have a motion of particles as independent random walks, and they interact only when they hit at the same position when where other particles are. So, but in more general case, we didn't consider that, but I will tell you later some property which will let you understand whether you can work with other models as well. Okay?
Okay, but I think that Pierre Del Moral works a lot with such particle systems and consider different limits because he studied idea to solve the Chi equation, filtering equation, using such particle approximations. Yeah.
Okay,
So,
it is just now for me, I mean, in terms of this project, it is just different model that could be also interesting to answer the question, what you can say about the central limit theorem. The simple symmetric exclusion process, I would say that it is a classical model of the interacting particle systems. And so it is a really, so there are many works devoted to different properties of the simple symmetric exclusion process. And our choice was because, first of all, the rate of convergence was not known. And the second, it is indeed simple model to work with. So only it was our motivation for.
Okay, let's go further.
Okay. About the equilibrium case, it is well known that if you assume that every particle at the beginning so appears with independent, with Bernoulli distribution, with a fixed parameter rho 0, that is between 0 and 1, then this distribution is an invariant for the dynamic. So it means that if your particle starts with a Bernoulli distribution, that for every fixed t, nothing is changing. And in this case, the situation is much simpler because so immediately you can say about some properties. For instance, the expectation is not changed, just the variance of particles is not changed. And this situation is much simpler to study. We would like to focus on the non-equilibrium case, where we assume that now we have a function which is defined on the d-dimensional torus and takes values in 0, 1. And this function so will describe the limiting profile of the particle system. And now you assume that at the beginning, the particles also have independent Bernoulli distribution, but now with parameter that is different from point to point. So now this measure is not invariant anymore. However, if you consider a small ball and make n very large, then actually in a ball your function rho is not changed so much. For instance, if you assume that rho is a smooth function, so therefore locally. So you actually start from the invariant distribution. But if you consider two different balls, then the value of rho can be very different. So in global, so it is not an invariant distribution. And for this case, for instance, it is not clear what is the expectation for the particles. And so let me just show you how we can compute in this case the expectation of or mean of particles, because later I will focus on this case and the expectation also will be important for me. Expectation I will denote by the function rho with index n. And it is defined on the discrete torus. And now, so everything what you need to do, you just need to say or use the fact that eta satisfies the martingale problem with the generator, which we precisely know. Therefore, you just need to compute the expectation, and you will and computing expectation, you will get rho, and then also you will have the expectation of the generator, which is applied to the function, which compute the value of eta at point x. And now using the form of the generator, you will have this difference. And you see that this difference actually is not zero, or can or let me say as follows: this difference is equal to zero when this x is not x and x plus the next point on the grid, because we don't touch all points of eta, so except these 2 points. So therefore, the difference must be the same, and it remains only 2 cases. And when you carefully write them, you will get this expression. And you see that it is nothing else as a discrete generator. And now, if you define the empirical distribution, which I will denote by tilde. So it is the empirical distribution associated with the mean of particles. Then you see that if you integrate just a function with respect to this empirical distribution, then this must satisfy this expression. And now when you pass to the limit, you can see that, this measure converges to the measure whose density satisfies the heat equation with the initial distribution, which is the profile that we considered before. And now a similar situation is also for the case when you now consider not mean behavior, but you consider the evolution of particles. So if you assume also that you have this initial profile, the same assumption for the initial distribution, and if you consider the empirical distribution associated with the particle system, then one can show that you have this process which will converge to the measure valued process in probability, where the density satisfies the same heat equation. Actually, it is the law of large numbers for a simple symmetric exclusion process, and it is known for many years. And let me tell you a few words why you should believe that this result is true. And to understand that, you just need to take a look on the generator first. So, and let me consider apply the generator to the cylindrical function. So you just take some function f, you integrate some another function phi with respect to the empirical distribution, and then you apply the generator. So you will have this expression. And now we apply the Taylor formula to the function f with the center at this point. Therefore, what you will see the first derivative, then you will see the difference of
I'm
this
sorry.
integral.
I'm sorry. Do write something now?
No, I don't write. I just show the. You should see the generator, and I show it. Do you see?
Now yes, I see. Okay.
Okay, good. So therefore, you see that you will get f prime. Then you will see the discrete Laplacian. It is precisely the term that was before. Then you will see the second derivative, and then you will see this difference to the square. But when you do the careful computations, you will get the following. You will have one additional constant here. Then you will have the discrete first derivative to the square. And then you will see the following expression. You just need to take your empirical distribution, but you need to shift all points, plus that the original empirical distribution, and then minus 2. And first you need to multiply this configuration with shifted one, and then take the empirical distribution. So you will have some expression which makes nice sense, and then you will have plus some the terms of other orders. And now everything what you need to do, you just need to test your eta by the function phi, and then see that, okay, it is like a term of bounded variation, which actually you precisely know what it is from this expression, because you need to take the function f that is equal to x, and you will have this term, I put it here, plus martingale. But the quadratic variation of this martingale is given by this term. And now you see when you pass to the limit, actually these terms goes to the term in the heat equation, and the quadratic variation goes to 0. So therefore the martingale part is vanished. And then you can conclude using also the tightness argument that what is going on? Can you hear me?
Yes.
Okay. Using the tightness argument, you can conclude that that actually, or you can believe that you have the convergence to a solution of the heat equation. Okay, now the next step could be what is about the central limit theorem. What we can say about the fluctuations of the simple symmetric exclusion process around its mean. So therefore, we just consider the difference, just the particle system minus expectation, and then we normalize by this constant. And then also, let's consider the empirical distribution, and let's do the same trick which we did on the previous slide. Oh, what you will have here, so therefore just you see that applying the generator to that to the cylindrical function where you test the fluctuation field. So you can rewrite this like that because the fluctuation field, it is a difference. And actually now you need to apply the generator to eta and the generator to rho, which is the discrete Laplacian for rho. And then doing a careful computations, you will see also the same term, also the first derivative, and then the discrete Laplacian here. But when you compute the second derivative, you see that you will compute the second derivative with respect to this complete argument. So therefore, you will get additionally to n plus 1 to the power d. And this term, it was, you saw on the previous slide, they will be cancelled. And then you will get the term which doesn't have, sorry, which have nothing that can vanish. So, and again, you can test the fluctuation field by a test function, and you will come to the following expression that this process is a semi-martingale with this term of bounded variation, and with a martingale which has this quadratic variation. And now if you believe that eta converges to rho, so therefore you will see here something like rho plus rho minus 2 rho squared. And you can predict what the limit is, and you can at least formulate the following theorem. And then using the tightness argument, you can prove it. Or therefore, for instance, due to that this work, So we can say that the fluctuation field converge in the space of distributions to a solution of this linear with respect to zeta stochastic partial differential equation. And a solution to this equation, it is a Gaussian process with the initial distribution, which is centered, and its covariance operator is given by this expression. So, any questions up to now? Okay, let me say now a few words about the idea of proof, because actually it will motivate about the rate, give some motivation about the rate of convergence. So as I already said, that when you consider the fluctuation field of the particle system, it is a semi-martingale with this quadratic variation. And now here you see that actually you know that if you take the empirical distribution eta and test by some smooth function, it converges to a solution of the heat equation that is tested by the same function because of the law of large numbers. So therefore, actually, this term here tested by this function and this term here tested by that function, they are not problematic. Only the problem can appear when you multiply. So here, eta and shifted eta. But to work with this term, we can use just the fact that eta actually it is the mean plus the fluctuation divided by this normalizing constant. And when you open the brackets, you will have something like that. So therefore, this term tested by phi, it is nice object. You should not worry about that. And now when you consider, for instance, this term, and you will test by this function, it is not also, we don't also have here a problem because you can move this rho to the test function. If you assume that your initial profile is smooth enough, so actually you also expect some regularity for the function rho n, and you have like a distribution or the fluctuation field which converges to the distribution, and you test by function which is nice. So therefore, in the limit, also everything is fine. Only the problem is with this term when you test by function phi. But here you can, this term, so you can rewrite as the product of this 2-point difference. And it is known that you can nicely control this. So therefore, you can control this term using the properties of path of the simple symmetric exclusion process. And it was the main idea how you can prove the central limit theorem. I didn't say that also you need to use the tightness argument, you need to use the Holly-Strouk theory for the existence of solutions to these infinite dimensional stochastic partial differential equations, but actually combining so this idea with the technique that I said, you can come to the final result. The problem only is that when you want to, that the tightness argument, it doesn't give the rate of convergence. And we need to do something else to understand how fast, so it, the fluctuation field converge to the solution of, to the generalized Ornstein-Uhlenbeck process. So actually we want to answer the question, how fast, this difference goes to zero. So the main problem here is that actually you have objects which are defined on the different probability spaces, and you cannot write this difference. It doesn't make sense. Everything what you can do, you can test your fluctuation field by some function. You can test the generalized Ornstein-Uhlenbeck process by the same function, then compute the expectation and compare the difference, or see how fast the difference converges to zero. And it is exactly what we will do. So we want to understand how fast this supremum goes to zero. And as I already said, the tightness argument and the Holly-Strouk theory, which was used before for the central limit theorem, cannot give the rate of convergence. Here, I would like also to mention a few results also in the direction of the quantitative central limit theorem. For instance, recently Gess and Zank considered or studied the higher order fluctuations for fluctuation expansion for nonlinear stochastic partial differential equation. But in their case, they worked with some family of equations which were driven by the same white noise, and they were defined on the same probability space. So therefore, here they use this fact a lot, and this approach cannot be applied to our case. Also, there is a work of Julian Fisher and Nikolai Perkovsky, who studied the higher order approximation of Dean-Kawasaki equation using the independent particle systems. And here they used the duality approach. Actually, when you have the independent particle system, you also can easily build a dual process. And this dual process was the key object or key tool in their argument. The approach that they used, it is really very sensitive, for instance, to the type of noise or to the behavior of the particle system. And so also we are not sure that the same argument can be applied in our case. Also, we found a work about the weak quantitative propagation of chaos and also the central limit theorem for Smoluchowski coagulation model, where authors use the properties or the expansion of generators, or they compare the generator to compare the processes. And actually, we will use the same approach which was applied here, but now we work in a much more complicated case than it was in these two works. So actually, we had to work much harder to be able to find or to prove the rate of convergence. And now the idea of proof is the following. Actually, it is the equality which probably you all know. If you, for instance, read the book of A.T. Kurtz, just on the first pages, you can find the following, that namely, if you have two Markov processes which are defined, which takes values on the same state space, and also started from the same initial conditions, then you can compare the expectation of this difference, so via the difference of the generators. And just using the fact that actually that the semi-group, it is the expectation of function of the process, we also can replace this P by the expectation. And therefore, we need to do the following. We need to compare the generators on the semi-group associated with one process. We need to do this comparison pointwise. Then we will get some constants which depends on the points where you compare the generators. Then you need to plug in your second process, and then you need to take the expectation and also integrate with respect to S. And if you can control this everything, then you can control this difference. So actually, it is the idea. And now having this idea, we can prove the following statement. We can show that if the initial profile is smooth enough, if also you are in the non-equilibrium case, and so this is the fluctuation field, this is the mean behavior of the process, this is a solution to that, this is the generalized Ornstein-Uhlenbeck process. Then you can claim the following, that this difference goes to zero, so with this rate of convergence. So for every good enough function f and also cylinder function phi, so which also you also can consider more than one.
What means smooth enough?
Smooth enough, here actually it means that it is differentiable probably d plus 3 times. I didn't specify the constant here on slide, but in our manuscript it is specified.
So d plus more.
There is something like, if I'm not mistaken, either d plus 3 or 3d plus 1, something like that.
I see.
That depends on the dimension of the torus. And also, I want to say that this speed of convergence is the optimal one. Here you can see that it is actually the sum of two errors. It is error 1 over n and 1 over n to the power d divided by 2. Actually, this rate of convergence that we call as a particle approximation error, actually it is what you expect in the central limit theorem. But this 1 over n, why it appears? And it appears because you initially work on the lattice, and then you want to approximate a continuous object. And therefore, it is an error which appears because of the comparison of discrete and continuous objects. For instance, you saw that when we considered the generator for the simple symmetric exclusion process, then you saw the discrete Laplacians or discrete derivatives. But in the limit, you have continuous derivatives. And when you compare them on the smooth functions, the error is independent on the dimension, and it is 1 over n. And it is exactly what we see when we compare these two objects. So therefore, we believe that it cannot be improved. 1 over n must be here when you compare the fluctuation field with the generalized Ornstein-Uhlenbeck process. Now, let me tell you about the proof and about the application of our idea or this formula. First of all, I would like to note that you can use this equality when you have processes which started from the same initial condition. So therefore, but now I would like to say that first, this process itself, it is not a Markov process. So to have a Markov process, we need to consider the vector, or we need to consider the information about mean behavior and also information about fluctuations. We do the same here. And now to make them to start with the same initial conditions, we do the following. We just consider a new Ornstein-Uhlenbeck process and a solution to the heat equation, which starts from the same initial conditions as the particle configuration. And then we compare the particle system with this process, because they started with the same initial condition. And then we compare two continuous in space and in time processes. This comparison, the second one, it should be simpler one, because everything what you need to do, you need to compare solutions to the same stochastic partial differential equation started from different initial conditions. So actually, so here should not be a big problem. Only the problem is to compare so these two objects in the first case, to compare two dynamics started from the same initial condition. And now, according to this formula, you see that you need to compare the generator on the semigroup associated with one of the processes. We will choose the Ornstein-Uhlenbeck process, and we want to consider the semigroup here, the semigroup associated with the Ornstein-Uhlenbeck process. When you consider that f is a cylindrical function, it is not necessarily that the semigroup also is a cylindrical function. But as a first step, let me show you what happens when we want to compare the generator on the cylindrical functions. So now I consider the functions which depends on two cylinders, one for ρ, another for the fluctuation field. And let's see on the difference of generators. So this is the expansion of the generator for the particle system. Here you can see also one additional term because you put one additional process here. And also you consider the generator for the Ornstein-Uhlenbeck process. And now when you consider the difference, also using this equality which we discussed before, and doing a careful comparison, you can see the following. For instance, when you compare this term and that term, I'm sorry, and that term, you will see actually the derivatives of the functions of your test function. So therefore, there should be the error 1 over n, and then multiplied by the constants, which depends on the supremum norm of the derivatives. Then, for instance, when you compare, for instance, this term, the red term with this red term, and using this expansion, actually this row which you will see here will cancel it with this row which appears. So, and therefore you just will need to care about that types of terms. But for instance, you can see, so in this comparison, this term. So let me show where it is. It is when you take this term, you will integrate it with this function. So it is exactly written here. And then it is not clear actually what you can do further with that term. You will have something like that where you integrate your row, this test function, with respect to the empirical distribution. Also, you see that term which will appear, and it is written like that. So therefore, the difference will have many terms here. I just put off a few of them, but after that, so let's see which problems appears. So first of all, as I already said, this function on which we want to do the comparison, actually we want to compare the generators on the semigroup, which is not a cylindrical function when your f is a cylindrical function. So it is the first problem. So therefore, this computation probably doesn't make so much sense for us. But maybe you can do the comparison of these generators on the functions which is smooth on some infinite dimensional space. And here also it is a problem, because this U it appears as a semigroup associated with this stochastic partial differential equation. And you want to have the smoothness with respect to rho and with respect to zeta. And for instance, the SPD has this term, the square root, that also can create problems about the differentiability. And for instance, when you consider the differentiability on the empirical distribution of this semigroup, actually it is not differentiable also. So you see the problem here. One more problem is when you want to control this term, now you cannot control via this via the expectation of product of these differences without losing the optimality of rate of convergence. And also it is not clear, for instance, what to do with that term, because actually you see that you plug in after the comparison, you need to plug in your process, but you need to plug in the empirical distribution. Rho is an empirical distribution and zeta is empirical distribution. So therefore, this term also doesn't make so much sense. And so when you want to directly use the formula which I showed, it is completely unclear what you have to do in, so with that everything what you have. So therefore, we need to have some additional idea which would which would help us to apply so this idea of comparison of processes via comparison of generators. And now I would like to come to that. I would like to come to the key idea which allows to make the right computations. And here the idea is that probably we need to replace the empirical distributions for or this way of lifting, how we lift the particle systems to the distributions, by something else. And our idea was to try to replace it by the smooth interpolation. Oh, and to do that, let's do the following. You remember that our particle that particle configurations are described by functions which are defined on the discrete torus. So therefore, let me introduce a Hilbert space L2 of all functions on the discrete torus with the discrete inner product. Also consider also L2 space of two differentiable functions on the continuous torus with this inner product. And now let's note that actually when you consider the standard basis it is a basis for two spaces, for the discrete space and also for the continuous space. And also they are eigenvalues for eigenvectors for the discrete and continuous differential operator. So in particular, so we know that if you consider a function which is defined on the discrete torus, you can expand it or write the Fourier expansion using this basis. But here you need to sum over the box of size 2n plus 1, so in every direction. And the same happens for the functions defined in on the continuous torus. But here you see you need to sum over all indices. And now we can use this to propose or to write this smooth interpolation. Actually, you see that this side, or here, what happens? So this one, it is defined, well defined, not only on the discrete torus or the points of the grid, but for all points of the continuous torus. So therefore, we define the extension of rho like this sum. And also, let's define its companion, which we denote by projection. We just take a usual Fourier expansion and we cut off it. So please note that here we take the discrete inner product that is defined for the functions on the discrete torus. Here we compute the continuous inner product. And now having these two operations, actually you can prove many nice properties. For instance, as we already said, this is the interpolation. This is the extension rho. It is infinite dimensional, so it is smooth function. Also, the projection, it is well defined not only for L2 functions, but for functions on the Sobolev space. Also, there is a nice connection between a discrete inner product and continuous inner product. For instance, when you have two functions defined on the discrete torus, you can write it via the continuous, I mean the discrete inner product, you can write via continuous inner product applied to the extension of these functions. Or you can switch between two inner products using Z equality. Also, you can nicely control, I mean, so these expressions and do so many other things. Also, I would like to say that, look, when you integrate the test function with respect to empirical distribution, it is the same as that you just consider this test function on the discrete torus, and you just compute the discrete inner product. Moreover, you can compare so this one you can compare with the continuous inner product, apply it to the test function phi, and the extension of rho up to some error where error depends on the fact how smooth test function is. So therefore, actually, the object that we started at the beginning, so it is not far away from the object if so from the extension of the particle configuration tested by the function phi and computed the L2 inner product. Also, I would like to say, I will not probably here go to the details. I would like to say that the Fourier basis also is eigenvectors for discrete and continuous operators. Therefore, you can also nicely compare the discrete differential operators and continuous. For instance, when you take a function which is smooth enough, say, then or has, for instance, okay, let's assume it is smooth enough. Take a projection, just project it. And then consider it on the discrete torus, compute the discrete Laplacian, and then lift it or consider the interpolation. It is close to the projection of the usual Laplacian, but since the projection of function is close to the function itself, actually this term is close to the Laplacian, and you can control nicely the error. So therefore, now having this extension projection operator, you can get, you can control many terms nicely I mean the terms which appears when we compare the generator. So therefore, now let's consider the cylindrical function, but instead of the empirical distribution, you consider this extension operator. And then you test it by a function, compute L2 inner product. Using the connection between discrete and continuous inner product, it is the same that you just compute here the discrete inner products of your particle configurations tested by projection of functions. And now when you will go to the expansion of the generator for the particle system, you will see the same terms which we saw before. But before you saw the integration with respect to the empirical distribution, but we said that it is the same that we compute the continuous, the discrete inner product. So I just put it here. But this discrete inner product now, I mean, now you need to consider the projections of functions because you see that you test by projections. And now using the connection between discrete and continuous inner products, you can put extensions. So therefore, you see that you started. So here you started from the generator of the points where you took extensions, and also all terms also have these extensions of the particle configuration. So actually the same point that in the left-hand side. And now when you will do the comparison of generators, actually now you don't have the empirical distributions, but you have the inner products between this extension of functions. So now you will see something like, for instance, I said that last time this term was problematic because a priori this should be a distribution that also was a distribution, and it was not clear what is that the integration of distribution with respect to distribution. But now you have L2 inner product of one smooth function, which will converge to the distribution, and actually another smooth function. And also, so everything is so nice with every term. And now I just here also say a few words that now actually you can control the problematic terms of, for instance, this term can be controlled via the Sobolev norms. The positive or so here, or you can control this via the derivatives of the order J, and this term, it can be controlled via the Sobolev norm. You actually can split everything. And also, by the way, now we can compare the generators also on the functions which are smooth enough on the Sobolev spaces. Oh, and now just let me say that I will denote the mth derivative of the function defined on the Sobolev space like that, and it can be identified with multilinear continuous operator. And for instance, when you compute the first derivative of the cylindrical function of this form, you will see the first you will see the derivative of the function f multiplied by this cylindrical function, and then you integrate the direction in which you compute the derivative. The same expression you have for the second derivative, and so on. And now when you consider this expansion of the generator for the particle system on the cylindrical function, you saw something like that. But where you see, for instance, the derivative of function f, and then you compute the Laplacian applied to this projection of the function psi. And also here you also see the derivative Laplacian applied to also the projection of this function, which is, I mean, this cylinder, and so on. But this is nothing else as just the derivative, the first, second derivatives, and so on. And now you can get also a similar expansion, not only for the cylindrical function, but for smooth enough functions on the Sobolev spaces. And now, so when we can compare the generators on smooth functions defined on Sobolev spaces, everything what you need to care, you need to show that actually your semigroup associated with Ornstein-Uhlenbeck process, it is also smooth enough, and then you can compare generators also on this function. Let me recall that we work with the solution to the heat equation. We work with the solution of Ornstein-Uhlenbeck process. Also, let's assume that initial distribution, it is the function from the negative Sobolev space. This is the function which later we can take the initial condition as smooth as we want. And now let's define for function f. So denoted by u, it is the expectation of this function. It is exactly the semigroup associated with this process computed on the function f. And then you can, using the fact that you work with the Gaussian objects, you can prove actually the integration by parts formula. And no, let me say first of all that you need to care here about the differentiability with respect to these two arguments, with respect to the initial condition for psi and with respect to the initial condition of rho. The differentiability with respect to the initial condition of psi, it is not complicated problem because this equation is linear. The problem only is the differentiability of this object with respect to rho, because you see that this solution also depends on rho because it is here, but here you see the square root. You see Laplace, you see gradient, and also the square root, which is not the differentiable function. So therefore, you cannot say that, okay, probably just to get the differentiability of this one, we just study the differentiability of solutions to this equation with respect to the initial condition. And here we use the fact that this zeta is a Gaussian process. And we also know its covariance operator. And then the derivative with respect to this variable, it can be nicely computed, and also you can prove the precise expression, whereas the first derivative can be rewritten via the second derivative of the function f itself. So it looks like integration by parts formula for the Gaussian distributions. So and now you see that you just need to compute the derivative of the covariance operator for this solution, but here you don't have square root anymore. So this function, it is smooth, and here it should not be any problem with its differentiability. Here I wanted to say a few words about the idea of proof, but unfortunately I don't have a time. So therefore now when we put all computations together, we can say that, okay, so the expectation so this expectation can be compared via this integral, where we need to compare the generators on the semigroup, which is smooth function. We can compare generator on smooth functions. We get a constant, which will depend on the particle configurations. So therefore, you need to compare. You need to care about the expectations of these constants, which looks like that. So, and now everything what you need to use the properties of trajectories of the particle system to be able to show that they can be uniformly controlled in n by some constants, and then you will get the rate of convergence in the case if your discrete and continuous dynamics start from the same initial condition. The last step which you need to do, you just need to take a solution to this equation, which starts from the initial condition the same as a particle system, and you need to compare it with the original Ornstein-Uhlenbeck process. And so therefore, you just need to say something about this difference, but it is equivalent to the case that you need to compare just two semigroups on different points. But you know that these semigroups are already smooth enough, and then you can try to use something like Stein method, because you see that, okay, when you want to compare these functions with respect to these variables, it is not a problem because they are non-random objects, and you can use the mean value theorem. Everything what you need to care about the f so for z and z. It seems that here I forgot to take one additional expectation. I apologize for that. And then you can use something like Stein method. because here you see that here you have fluctuations of the particle system at the beginning. So and this so it's at 0 time you had just independent Bernoulli distributed random variables. You consider this extension, okay, and you want to compare this with a Gaussian distribution psi0 with this variance. And to do that comparison, actually, it is enough to compare this object or the function applied to this object with the function applied not to this distribution, but to the projection, because we nicely can compare projection and the original distribution. So therefore, we compare only these objects. But you see, but now they are finite dimensional. Because they are finite dimensional, because this expansion can be written in the Fourier series with finite number of coefficients, and projection also is the same with a similar Fourier series with the same number of coefficients. And now you can identify these two objects with vectors that have a finite number of coordinates. Everything what you need to care, you just need to care with the fact that you worked on the Sobolev spaces, and these functions and objects were defined on, so these functions were differentiable on the Sobolev spaces, objects were defined on Sobolev spaces, but now you want to identify them with vectors, so therefore you need to somehow good merge the topology which comes from the Sobolev space with the Euclidean topology. So therefore, we consider not only coefficients itself, but we normalize them by some constant. And then we compare the functions, and then we compare these objects. But here you can use the Stein methods, which is available in the literature. Just compare this one. And after that, you just need to understand that all constants which you get can be nicely rewritten via the derivatives of the functions, of the original functions, which gives you immediately the possibility of this comparison. So if so that you want to know more how we prove everything and so on, you can find this in this work which recently appeared in arXiv. And here also I put a few of papers which also I mentioned. That I took some results from that papers and mentioned them today. Okay, thank you so much for your attention.
Vitaly, thank you very much for interesting talk. And I think that somebody have questions and comments, please.
What it means hydrodynamic limit? Few words about it.
Yeah, sure. So it means that so actually, as I know, so there could be two regime, or mean field limit or hydrodynamical limit. In the hydrodynamical limit, so actually, what you have, you can consider one box, so say of some radius, probably small one. And then you consider, so enlarge when you have more and when you have a lot of particles. And then in every box, you have so many particles. So and then you care about their their average behavior on this box. So actually, you consider not every particle itself, but you consider this profile in average. And when you pass to the limit, so actually you should expect that you have a convergence to some nice function. So it is when people talk about the hydrodynamical limit. When you consider the mean field limit, so actually you have more particles on the space, and then you just consider the empirical distribution, and also you test by functions. So, but and then you can also pass to the limit. But
okay, thank you very much.
Okay, maybe other questions, please. Let me ask you two, because I have several questions. Firstly, about your semi-group of Ornstein-Uhlenbeck. Usually, when we consider Ornstein-Uhlenbeck semigroup in Gaussian setup, and you use the Gaussian integration by part formula, so you use partially at least Gaussian setup, we expect that Ornstein-Uhlenbeck has a very good properties. You have a hypercontractivity even property, so maybe for your process, you can also expect something like this. That if you have a function which is not differentiable, then applying this group, you will get a good differential function. Is it true or not in your case?
We never thought about in this direction, but actually here you see that okay, we compare the processes itself, and probably to get something like hypercontractivity and so on, you also want to know something what happens, roughly speaking, with derivatives and so on. But maybe it makes sense. Maybe you also can include something additional about the behavior of process.
I've seen such, so there are very popular inequalities related to this. For example, you can find in Bogatyov's book on Gaussian measures even way applying properties of Ornstein-Uhlenbeck to get a logarithmic Sobolev or Poincare inequality. So maybe such additional knowledge can be useful for you. Just get knowledge about smoothness of functions where you apply generator. This is a first question. The second one. Now I understand clearly why you use the lattice, because of this very nice idea to build discrete Laplacian and continuous Laplacian using actually characters on the group of motions on the lattice. So let me recall you that there are a lot of work, by the way, also Grigorchuk, who you know about the random motions on the groups. And so I think that if you use characters, you can do exactly the same. So maybe it is good to see some generalization which are infinitely dimensional of the torus.
Thank you so much for that comment. We never thought about in this direction. We thought about the generalization in other direction in terms of that possibility of choosing of other models. For instance, zero range process. But actually, you see that here it was very important that you can consider that you have a possibility to consider two generators. And if you see the terms which are close, which terms of one generator are close to terms of another generator, that actually you should hope that you can be successful in the application of that of this idea. But for instance, for zero range process, there also, when you prove, for instance, the central limit theorem, you need to use something like replacement lemma, because now your generator is not anymore linear as with respect to the particle configuration as the simple symmetric exclusion process. So therefore, this idea of averaging that I said in the hydrodynamical limit, you need to compute the function of every configuration. Then you want to be sure that this average of functions you can replace by function of the complete average. And when you can do that, then you can prove the central limit theorem. But you cannot see this on the level of generator. So therefore, we thought how we can overcome this problem when you also need to apply that the replacement lemma or something like that in the case of nonlinear generators for the particle system. But also it is very nice idea about
in this
way.
context, let me recall you the book of Sandra Tserai. And actually, she did approximation with Wright-Fisher model to the same equation as you did, but with square root without 1 minus ROT on the interval 0, 1. So she has convergence, she has a lot of estimation in this book. It will be valued just to check it. The last one is the following. Usually, when we consider such particles approximation of some continuous motion on the compact space, it occurs that if we start from non-equilibrium, and then of course we have ergodicity, and of course when t grows we have the rate of convergence to equilibrium, and when t and n number of particles goes simultaneously to infinity, we see such a cutoff effect, which was studied maybe from Duret in 2005, yeah, which says that from some time, which depends like n logarithm n, we get very good approximation to in Wasserstein distance to the ergodic distribution, yeah. So I think that if you consider the same picture in your considerations, you can get a nice central limit theorem when n and t simultaneously goes to zero, to infinity. Yeah.
Also, so we thought about the uniform because everything what you want to prove, it is just takes the supremum for all t, but not from the interval. It would be also the same that you said.
My point is that it will be not supremum. My point is that when t goes to zero together with n, but in a special way, you will get much more better estimation.
Okay. Okay. I understand.
Okay. Thank you again for very nice talk. And who will be next speaker, Georgi?
Next will be Alexei Rudenko.
Okay.
We talk about Brownian motions on the Carnot group.
And last, what I have to say is that tomorrow at our department meeting, we also have Vitalii talk about his doctor's thesis. So everybody is welcome. Okay.
But by the way, I prepared it in Ukrainian.
Oh, I see. I see.
So one should mention because so I knew that I have to do that in Ukrainian, and I don't have no time to translate it.
Yeah.
I can speak
But
English.
at least participants from Ukraine can meet Vitalii tomorrow too. Okay.
Okay.
Then thanks everybody, and congratulations with the beginning of our work. Thanks Vitalii, and see you next week. Bye.
Okay, bye.
Thank you.
Thank you.
Bye-bye.
Bye.